So rational functions are created by the quotient of two polynomial functions. You're going to have some polynomial p on top and some polynomial q on the bottom. Again, like I said, I'm using a specific color code on purpose. I would follow along with my color code today. Huh? It's orange, yes. P and Q are polynomial functions, and since we just made a fraction, we know that the denominator cannot equal 0. That's a huge bit of information for us because we now have to change the domain of our function to exclude the values that make Q equal to 0. Meaning, instead of just saying this function has a domain of all real numbers like we were able to with all of our polynomials, we're going to have to take numbers out of our number line that are no longer allowed to be used. And it's anywhere that the denominator would be equal to 0. So to find the domain of this function, I really don't care about the numerator right now when I'm talking about the domain of a function. All I'm going to do is take the denominator and set it not equal to 0. So I'm going to say x minus 3 cannot equal 0. So what number can x not be? 3. Great. So if I make a number line for all of those numbers from negative infinity to infinity, I can use every single number on here except for the number 3. That's the only number I cannot use in my domain. So if we're writing this in interval notation, what would it look like? Negative infinity, keep going, to 3, union, or 3 to infinity. That's the domain of this rational function. We can use every single number except for the number that makes the denominator 0. Yes? Cool. Let's try the next one. Here's the g of x function. Do I care about the numerator?
No.
Not right now. Do I care about the denominator?
Yeah.
Yes. I need to know what numbers would make this equal to 0. So you can factor this, which does make a future problem a lot easier for us. Yes, we recognize that it's the difference of two squares. So this is x minus 3, x plus 3. That's what we don't want to be equal to 0. Okay, so what I highlighted in orange is the same as what I wrote down in factored form. So what are the two numbers I'm not allowed to use? Negative 3 and positive 3. So, but we can use literally every number on this number line other than those two. So my number line, making sure I put these in number order with negative 3 going first, would be all of this and then a small gap at negative 3 and then a small gap at 3, and we can use everything else. What does the domain look like for this function?
Negative 3.
To negative 3. Union.
Negative 3 to 3.
Yes.
And union 3 to infinity.
Awesome. So we just cannot let the denominator equal to 0 because you can't divide by 0. So all we care about for the domain is making sure that denominator is not 0. Questions, comments, concerns? Okay, cool. What about the last one? Can you factor x squared plus 9?
Yes.
Are you sure?
Yeah.
X squared plus 9?
No. Oh, wait. What?
It's not the difference of two squares. So if you can't immediately factor, that's okay. What we can do is we can take that denominator and we can just set it not equal to 0. Okay, so you could have done this on the problem before this, you would have gotten the same answer. But if we can't think of how to factor, we can't factor, let's just go ahead and do this. Let's solve for x. What do I do to solve for x? Minus 9 on both sides. And then what? Square root. Now when you do the square root, what do you have to remember to put in front? Plus or minus. Now what is the square root of negative 9?
Oh, first imaginary.
I think everything everybody just said is yes. This is 3i, right? The negative becomes I when you take the square root, and then the square root of 9 is 3. So we have x equal to plus or minus 3i. So my question for you, on this number line from negative infinity to infinity, where do I put the numbers plus and minus 3i? You don't.
Because it's imaginary.
Because they're imaginary, which means I can use literally every single number I want down here. This domain is all real numbers from negative infinity to infinity. Yeah, the key here is that you can't plot an imaginary number on a real number line, and domains are all about the real number line. So if you get an imaginary answer, first maybe check your work, make sure that was supposed to happen, and 2, you have no restrictions on your domain. Yes?
Why can't we factor it? Like, isn't it negative times negative positive? So why can't we just do
Minus 3 plus, okay, that's a great question. I was going to answer it without writing something down.
Or no, positive.
So you're saying this because negative 3 times negative 3 is 9? I agree, but if I were to actually FOIL this, I'd have a middle term of negative 6x. So it's not exactly the same.
It would be same for positive?
Say it again?
It would be same for positive? Like we do plus 3.
Plus 3 and plus 3, yeah, you'd have a plus 3 in the center. Plus 6x.
She asked the question, how are we supposed to know?
Whether it factors or not? An easy rule of thumb is if it's small like that, you don't necessarily have to factor to do the domain. Like if I were to just solve this one the same way, x squared minus 9 equal to 0, you would add 9 to both sides.
Oh.
And this is plus or minus real 3, no I. And those are the two numbers we got when we factored. So in a pinch, set it not equal to 0 and solve for x.
So if it's so like if it's x squared plus something positive, it would be like we have to do what we did.
Yes, because it wouldn't factor. If it factors easily, factor it, because that's way faster probably for our brains. If it doesn't factor or you don't notice that it factors, you can just set it not equal to 0 and solve. That's a good question. How do we feel about the domains of these functions?
Confident now.
Great. Now, we're going to add more tools to our toolkit as we graph these rational functions. So that's the first one, that our domain has restrictions. There's going to be numbers we cannot use. But we also need to start discussing what's happening around those function values where there are discontinuities, meaning the numbers that you took out of your number line, something special happens there. And for the most part, the things that happens is that we have the function values that go off to one of the infinities. So if we start by looking at the really basic reciprocal function, this is 1 over x, it's like the most classic rational function. And we plug in a bunch of numbers as we get close to 0, because like if I put 0 in this denominator, wouldn't the denominator be 0? Okay, so if I try to plug in 0, it won't work. But what happens if I try to make numbers very, very close to 0? So I start at negative 1, get it smaller, get it smaller, get it smaller, get it smaller. This number is wildly close to 0. It's just on the left side of 0, right? What we are doing here is we are trying to see what's happening with the graph as we get closer to that undefined value. And if you notice, 1 over negative 1 is negative 1. 1 over 0.5 is negative 2. 1 over negative 0.1 is 10. What's happening to these numbers as I keep plugging in smaller values?
They get bigger.
They get bigger, but they get bigger negatively, so they actually get very small. But it's a big negative number, which is the wrong way to think about it, but I see why our brains think about it like that. It's a big number, happens to be negative. Okay. That means we're going down, 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 okay? The way we're going to talk about this, and if you took AP Pre-Cal last year, we used limit notation. We're just going to use arrow notation in this class, so it's a little less. We're going to describe what's happening to the values of the function as x approaches 0 from the left. That's how you would say this. As x is getting closer to 0 from the left side. This is the left side of 0, right? What is happening to the function? The function is going down. So you would say negative infinity. To pronounce this correctly, you would say as x approaches 0 from the left, f of x approaches negative infinity. That's what you would say out loud. This is a limit, just not written in limit notation. Let's see what happens as we approach for the same function from the right. So if you flip it over. If we look at these numbers getting closer from the right, so we start at 1, then we do 0.5 and 0.1, 0.01, 0.001. Isn't that getting closer to 0, but like the opposite direction? What's happening to these numbers as they get closer to 0? They're actually getting bigger, like legit bigger, not negatively bigger, because that's a weird concept, but actually bigger.
Yay.
That means that our our arrow notation is going to say as we approach x from the positive side of 0, from the right side of 0, our function values are going up. My arrow would be going up. Okay, these different directions that the graph is going is going to be very important for some other things we're adding when we talk about rational functions. We also need to talk about what happens to these function values as x gets further away from the origin, both directions. So if you see I have a table and here are my x values this time, just getting like ridiculously small if you look at it this way. And that might be helpful to put an arrow like this and then like this, right? So if 0 was in the center, As we get smaller, what are happening to my values of numbers? Are they getting bigger or getting smaller?
Small.
But they're getting closer to what number? 0. As I plug in bigger values for x, what am I also getting closer and closer to? 0. This is called the end behavior of the function. This is what happens as x approaches negative infinity or x approaches positive infinity. Our function is going to get closer to a number and like flatten out at that particular number. Okay?
So it'll never hit 0?
It never will hit 0.
Okay.
It's going to get very, very close to, but never actually happen. Yes? Okay. Now I have another picture of a graph here just for reference. The book used this as an additional reference because it's pretty important. So we can still talk about the different arrow notations as we get closer to different values. So as we get closer and closer to negative infinity, what is this graph flattening out at? What level?
What do you mean?
Like what flat number? Look at what my hands are doing. This direction.
Yeah.
Yes, it's getting closer to 0. What about on the right side? 0. So we're saying as x is approaching positive and negative infinity, our function is approaching 0. We're flattening out at the number 0. What happens as I approach the number 0 on the x-axis from the left side? Where is this arrow going? Positive infinity. What about on the right side of 0? Same thing. So we have different combinations of numbers and directions that can occur with our rational functions. So our job is to make sure we understand what direction our arrows should go as we graph these functions. Okay, but what is exactly happening when we're drawing all of these arrows? Thank you so much for asking. Let's turn the page. These are called vertical asymptotes. A vertical asymptote is an invisible vertical line that the graph is going to get very, very close to, but is never going to touch. I'm still using orange on purpose, by the way. A vertical asymptote is the line that those graphs are getting closer and closer to when we were writing those limit statements. So if you see at A, there's like an invisible boundary line for this function that f is going to get close to but never touch. It's going to like scoot out to positive infinity. And on the left side, it can scoot out to positive infinity. Or maybe it's negative infinity. Or maybe it's negative infinity from the other side. These lines that we're like skimming, we're not actually touching them, but we're getting really, really close to, are called vertical asymptotes. That is what we're finding when we're talking about these arrow statements. This is what we're finding when we set the denominator not equal to 0. Those places that you had discontinuities from the very first page is going to be where these functions have actual vertical asymptotes. That was actually what we're finding. So again, our vertical asymptotes come from the rational function in which p and q have no common factors remaining, and it's a 0 of that particular quotient in the bottom. Not quotient, denominator in the bottom. Okay, so your number that you found when you set the denominator not equal to 0 is the location of your vertical asymptote. Okay, before I read the rest of that theorem right there, let's look at an example so you can see. We've already kind of seen this function, but if we have f of x right here, I want us to be more comfortable factoring for this kind of problem. If we rewrite f of x in fully factored form, the top does not factor because it's just a plain x, but the bottom is the difference of two squares, so we would factor to x minus 3, x plus 3. When it comes to vertical asymptotes, I need to make sure they don't cancel out of the function. Does anything cancel top and bottom? No, so we're good. At this point, what you would do is you would take the entire denominator and you'd say this is the stuff that cannot equal 0 because it's the location of the vertical asymptotes. So you would have a vertical asymptote, VA, I'm lazy, is that okay with everybody? Okay, you're gonna have a vertical asymptote at x equal to 3 and at x equal to negative 3. Because those are the two numbers that I cannot plug into the denominator. Those are the two numbers that are the location of my vertical asymptotes, which is what this question is wanting us to find. The equation of the vertical asymptotes. Does that make sense? Okay, let's look at example B. If we go to factor the g of x function, it's the same thing. So we know that the bottom is going to factor to x minus 3 and x plus 3. But this time, we can't just ignore the numerator. We can ignore the numerator when it's just asking for the domain. But this time, when I go to look at the things that are left in the denominator, do you see that x plus 3 on top and x plus 3 on bottom would cancel each other out? That is not a vertical asymptote. It's a hole in the function. So this is our second type of discontinuity that's maybe not as popular with a lot of functions, but if you have common factors between P and Q, common factors, the things you can cancel out when things are in factored form, that means that that is actually a hole. It is not a vertical asymptote. So if I were to list the vertical asymptotes for the g of x function, I would say that it only has a vertical asymptote at x equal to 3. Not at negative 3, because at x equal to negative 3, that's actually a hole in the graph, which this question technically didn't ask for, but we know that piece of information. If it cancels out, it creates a hole.
That has to be two numbers.
It has to be the same thing on top and bottom.
No, like for the asymptote.
No, not necessarily.
Oh.
You could not have a vertical asymptote.
Oh.
You could have 1, you could have 5, you could have 17. As long as that 0 is remaining in the denominator after you cancel out common factors, that creates a vertical asymptote. Okay, but what if we have the h of x function here? We did this earlier. Does this factor at all? No. So were there any moments that I had a piece of discontinuity in my domain?
No.
No, which means this function right here has no vertical asymptotes. Again, if you're wanting to be like, wait, why? Because if you look back later and you're like, what did we do here? We set this equal to 0, and we solved. We said that this was negative 3. Nope, skirt, just kidding, negative 9. And that x is equal to positive or negative 3i. And again, is 3i a location on a real graph? No, vertical asymptotes are only going to appear at real locations on a number line. So if you get a plus or minus I number, first of all, check your work. And second of all, there is no vertical asymptote for that particular graph. Okay. It is going to be important that you recognize the difference between vertical asymptotes and holes. The holes are the ones that cancel. So we do want to be able to factor these polynomials on top and polynomials on bottom before we really get started with our rational functions. Okay. So we had these horizontal asymptotes. That was one of the statements we drew with those arrows, is what's happening as we skirt up or skirt down along the graph. We also had two other types of those arrow statements we wrote, and these are called horizontal asymptotes. This is also known as the end behavior, and I'm going to accidentally call it that a lot because in AP Pre-Cal, that's what we usually are referring to as the end behavior. And since I teach that class, I get tongue-tied and I say the wrong things. But horizontal asymptotes are talking about the end behavior of the function. This is the line that the graph is going to flatten out at the very ends of the graph. Okay, a vertical asymptote you cannot cross no matter what. A horizontal asymptote you can cross in the middle because it's specifically designed to tell us about the end behavior, not middle behavior, end behavior. So if we notice, in the little pictures we have here, we have a horizontal asymptote for the first graph. Does it ever touch it? Does it get really close to it at the end of the graph? Fabulous. That's a horizontal asymptote. What about this one? Does it cross it? But does it get close at the end of the graph? Okay, this third one, that is a horizontal asymptote. And even though it crosses right here, that's okay. Because at the end of the graph, isn't my graph getting very, very close to that green highlighted line?
Yes.
Its end behavior is its horizontal asymptote. Finding the horizontal asymptote is very simple if you remember three things for me. Locating the horizontal asymptote has everything to do with the leading coefficient of both the numerator and the denominator. So right now, I want you to take your green highlighter and I want you to highlight the first, that's not a highlighter, that is a pen. I want you to highlight the first two terms in both the top polynomial and the bottom polynomial. If they're in standard form, you're just looking at the first number. If they're not in standard form, you're looking for the largest degree on top and the largest degree on bottom. The three acronyms I need you to know to make this very, very simple for you. The first one is called BOBO. Bobo, Bot, and Betsy. Bobo stands for bigger on bottom, 0. If your polynomial, or if your rational function has a bigger degree on bottom than it does on top, meaning this number is bigger than this number, your horizontal asymptote is 0. Period, the end. Bobo tells us that. Bigger on bottom, 0. The next one says that the numerator is bigger than the denominator. So this is called bottom. It stands for bigger on top, none. If it has a bigger degree on the top than on the bottom, there is no horizontal asymptote. We might have what's called a slant asymptote, which we'll talk about later. The last one is called Betsy. And those of you who took my class last year, do you remember what the C in Betsy stands for? Coefficients. We are going to divide the coefficients of those leading polynomials on top and bottom, meaning your answer is found by saying y equal to whatever the leading coefficient is divided by the leading coefficient. So a sub n, whatever it is on top, divided by whatever it is on bottom. Boom, that's the answer. We don't have to graph it. We don't have to do extra work. We just have to Bobo, Bot, and Betsy. Can I prove to you how easy this is? Okay. We're finding the horizontal asymptotes if there is one.
Okay.
We look at this function. What is the degree of the top? 1. What's the degree of the bottom?
2.
Where is it bigger?
2.
On bottom. So this is a Bobo graph because it's bigger on bottom.
Okay.
And Bobo tells me that the horizontal asymptote is at y equal to 0. The end.
That's it?
That's it. Bobo, Bot, and Betsy.
Yay.
What about the g of x function here? Is it Bobo, Bot, or Betsy? Betsy, because the degree of the bottom, 2, is the same as the degree of the top, 2. Now, Betsy tells me that I need to do a division of the coefficients. So if I was doing this, my horizontal asymptote, my end behavior, would be y equal to 4 over 2. But like we can totally actually divide those numbers. So my horizontal asymptote is going to be at y equal to 2. So again, all I did was take these two numbers, the leading coefficient of the top and bottom, and divided them. What about the last one? Is it Bobo, Bot, or Betsy?
No.
What's the degree of the top? 3. What's the degree of the bottom? So where is it bigger? It's bigger on top, which means what is the horizontal asymptote? There is no horizontal asymptote. Very good. So these lines that we're going to draw for our horizontal and vertical asymptotes give us guidelines on our graphs to create better rational functions. Bobo, Bot, and Betsy. We're going to stop there before we go to lunch because after lunch we're going to start graphing these functions. We're going to graph 3 of them together in a 6-part algorithm in 6 steps. Those 6 steps give us all the information we need to draw accurate rational functions. After lunch we got this. What's up?
There's a lot of space on this page.
Yep.
I don't like that.
Here's our strategy, our algorithm that we're going to use to graph some rational functions. Now again, our rational functions are made up of a polynomial on the top and a polynomial on the bottom. That color code is going to be important. The first thing you're going to do is you're going to determine whether the graph has any sort of symmetry. Yellow on purpose. What you're going to do is you're going to plug in negative x to the function. If you plug in negative x and it comes out exactly the same as you started, so it's the same, you have y-axis symmetry, that's called an even function. If you plug in negative x and the function changes all of the signs, so every positive becomes a negative and vice versa, that's called origin symmetry or an odd function. So we're going to check first for symmetry so that we can create additional points at the end very easily. Then you're going to find the y-intercept. The y-intercept for us today is going to be purple. You're going to find this y-intercept, if there is one, by evaluating f of 0, which means plugging in 0 to the function. Step 3 is to find the x-intercepts, if there are any, by solving the equation p of x equal to 0. Now, p of x, that's the numerator. So you're taking the numerator, setting it equal to 0, and solving for the places where the graph would cross the x-axis. You're going to look for any of the vertical asymptotes, or technically holes, by solving the equation q of x equal to 0. So that's the denominator equal to 0. Step 5 is to find the horizontal asymptote using one of the rules for determining that horizontal asymptote of a rational function. And just so you don't have to flip your page over, that is Bobo, Botten, and Betsy. That's what you're doing on that step for the horizontal asymptote. And then last but not least, you're going to find some additional points, at least 1 point beyond each x-intercept and vertical asymptote. So we're going to have to find some additional points to know where our graph belongs. It's pink, surrounding the x-intercept and vertical asymptotes. So sometimes that's finding 2 extra points, sometimes that's finding 3 or 4, just depends on the kind of question you have. Those are your six information steps. The 7th step is to play connect the dots. Once everything is on your graph, you should have enough information to correctly play connect the dots and graph your rational function. Can we do one together? We're going to do all 3 together. I don't know why I said it like that. But let's do one together. The first thing we're going to do, step 1, is work on symmetry. And that's yellow, and I know it's hard to see, but it follows my color scheme. So we're going to plug in negative x to the function, which means I'm doing 2 times negative x minus 1 divided by negative x minus 1. If I just simplify this down, 2 times negative x is negative 2x and then minus 1. And then this is negative x minus 1. Is that exactly the same as we started with?
No.
This yellow equation, does it match the black one? No. Is it exactly opposite? Did all of the signs change?
No.
No. So there is no symmetry for this graph, which stinks because the symmetry is very easy to use when we're plotting our additional points. So we have no symmetry. So for step 1, that would be our answer. There is no symmetry. Step 2 is to find the y-intercept. We're going to find the y-intercept by doing f of 0. F of 0 means plug 0 into the function. So this is going to be 2 times 0 minus 1 over 0 minus 1. Well, 2 times 0 is 0. 0 minus 1 is negative 1. I have negative 1 over negative 1, which is what? 1. So my y-intercept is 1. We find the x-intercepts by setting the numerator equal to 0 and solving. My numerator for this problem is 2x minus 1, so I'm going to take 2x minus 1, set it equal to 0, and solve. Add 1 to both sides, divide by 2. I have one x-intercept, and it occurs at 1/2. Are we following?
Yep.
So we did symmetry, we did y-intercept, we did x-intercept. Up next is to find the places where the graph would have a vertical asymptote or a hole by looking at where the denominator, wrong color, the denominator would be equal to 0. So if I say x minus 1 is equal to 0, what's the place that I have a vertical asymptote? At 1. So just for yourself, this is a vertical asymptote in case your color scheme got lost. We're at 4 of 6. For number 5, it's going to be talking about the end behavior or the horizontal asymptote. So if we look back at this equation, it's in fully factored form, so we're doing pretty good. Is this Bobo, Botten, or Betsy? Betsy, because it's the same degree on top, 1, as the degree is on bottom. Betsy tells me that my horizontal asymptote is going to be at the location of the what's that called? Leading coefficient on top divided by the leading coefficient on bottom. What's the leading coefficient of the top? 2. What's the leading coefficient of the bottom? 1. So 2 divided by 1 is 2. All right, fabulous. So we have that piece of information. The last thing, well, we've got 6 steps. So the last thing we need is some additional points on the different sides of the zeros and the vertical asymptotes. My recommendation is at this point, before you do the pink step, put all of your information that you know on the graph. Here's what that would look like. Number one, we have no symmetry, so I'm going to add no yellow to my graph.
Okay.
But I know that there is a y-intercept at 1, so I'm going to put a purple dot at 1 on the y-axis. I also know that there is an x-intercept at 1/2, so I'm going to go to 1/2 and I'm going to put a blue dot. I know that I have a vertical asymptote at 1. So I'm going to come in and I'm going to draw a vertical asymptote in orange on my graph on the line x equal to 1. I also know from the green step that I have a horizontal asymptote of 2. So I'm going to go horizontally on the line y equal to 2 and draw a horizontal asymptote. Now the pink step, I need values on each side of every 0 and every vertical asymptote. Here's a 0. Do I have a number on the other side of that 0? Like, do I have a coordinate point?
Yeah.
Yeah, okay, so that side's good. But on this side of the vertical asymptote, do I have any coordinate point?
No.
No, so we need to pick something to plug in. What's a nice, cute, easy number to use on this side? 2, great. What we're going to do is we're going to evaluate f of 2. We want to know what's happening to this function on the other side of the vertical asymptote, which means I'm just plugging 2 into the equation. This would be 2 times 2 minus 1 over 2 minus 1. 2 times 2 is 4. 2 minus 1 is 1. This is the number 3. So I have a coordinate point of 2, 3. So I'm going to plot the coordinate point 2, 3. Feels like that's not looking like anything until you start to play connect the dots. If I start connecting the dots where I have the most information, I have the most information right here. So if I connect those dots together, it's pretty obvious that as I get close to this vertical asymptote, I should be going down.
Yeah.
If I work backwards, that means I need to get close to but never cross the green line.
Okay.
There's the first bowl, inverted bowl of my graph. Now again, I need to go work where the most, those were not correct words. I need to look where the most pieces of information are now, which for me are right here. I need to be able to hit this coordinate point and not cross this green line. So it's going to look something like this, skimming outwards. And if I work backwards, it should go up. There's our rational function in 6 steps. We checked symmetry. We checked for the y-intercept. We checked for the x-intercept. We checked for the vertical asymptote, the end behavior, the horizontal asymptote, sorry, and any additional points. If you're wanting to make this look like we actually did a bunch of problems, if you want to put boxes around stuff, that's your y-intercept. This might be helpful for your notes since this is the first one. That's your y-intercept. This is your x-intercept. We already labeled this one as your vertical asymptote. Very good. And then we have a horizontal asymptote at y equal to 2 and an additional point at 2, 3. Before we ask questions, can we just try another one to see the process all one more time? And then I'll take questions.
I don't think we're supposed to.
Nah.
Could you?
Okay, here we go.
Okay.
What was the first thing we're checking here?
Axis symmetry.
We're looking for the axis of symmetry, and how do we find the axis of symmetries?
That's an amazing question.
We plug in negative x. So anywhere there was an x a second ago, I'm plugging in negative x. I know that yellow is hard to see. I'm so sorry. I don't normally write in yellow, but it's important. Now, what is negative x, in parentheses, squared? Just x squared, right?
Yeah.
So the top is just 3x squared. What about the bottom?
Wouldn't that be a squared minus 4?
X squared minus 4. Okay, compare what we got at the end of the yellow step to what we started with.
It's the same.
It's the same.
Yeah.
Since it's the same, that means it's an even function and that we have y-axis symmetry. So anything I plot on one side of the y-axis has an additional point on the other side of the y-axis. It should be foldable, basically, along the y-axis. Okay, great. What was up next? The y-intercept. How do you find the y-intercept? Plug in 0. So I have 3 times 0 squared over 0 squared minus 4, which is 0 over negative 4, which is 0. We have a y-intercept. After we get the y-intercept, what's next? X-intercepts. How did we find the x-intercepts? Put the numerator equal to 0. So I'm just doing 3x squared equal to 0. I divide by 3 on both sides. Why did I make that a cubed? I don't know. And then I take the square root of 0. What's the square root of 0? 0. Okay, so we have an x-intercept. Now, does this make sense that my x-intercept and my y-intercept are both 0? Yeah, that means I'm crossing at the origin, 0, 0. That happens.
It does.
Yes. Oh, I wrote too big. Step 4. What was step 4? Vertical asymptotes. I used the wrong color. It's not green, that's orange. Sorry. I'm so sorry. How did we find the... You know what? I'm going to sneak it over here since I just need some space. How do we find the vertical asymptotes? We set the denominator equal to 0. If I set that equal to 0, you could factor this to do the steps or just follow the same ideas, add 4 to both sides, and then we square root. What's the square root of 4? 2, but I need plus or minus since I took the square root of that number. So how many vertical asymptotes do I have here? 2. Okay, great. What's step 5?
Horizontal.
Okay, what are the 3 questions I asked myself?
Bobo, Betsy, or...
Botan. Bobo, Botan, or Betsy. So look at this equation. Is this one Bobo, Botan, or Betsy? Betsy. So I'm going to divide the coefficients for my horizontal asymptote, and where is it going to appear? At y equal to 3. Because it's a 3 on top and a 1 on bottom, so it's y equal to 3. All right. Got lots of things floating around here. At this point, again, before you start step 6, it's pretty helpful to put all of that information on the graph so you know where you need to find these additional points. Now, here's what I like to do with the yellow step that we did not have to do the time before. I want to highlight the y-axis to remind myself that this should flip over the y-axis because it's an even function. We should have symmetry on one side or the other. I know also that we have a y-intercept of 0. That's the wrong color. And an x-intercept of 0. I like putting both colors there. Can't help myself. My orange step is to add my vertical asymptotes, which are at -2 and +2. And then I want to add my horizontal asymptotes, again, end behavior, not middle behavior, end behavior. And that's going to be a flat line at 3. Okay, I want pieces of information on both sides of the vertical asymptotes, the zeros. Do I have, ooh, my iPad's about to die. I'm going to go sit up here. Do I have any information for the left side of this orange vertical asymptote that I'm about to point out as soon as I put this stuff down? Do I have any information over here?
No.
Okay, what number could we plug in that's like pretty easy to use? Sure, let's plug in -4. Now we're going to make our lives easier here, and hopefully somebody has a calculator on their desk. Let's go ahead and use a calculator to figure out this number. If we do f of -4, we're going to get some value out. And I want a decimal answer here because we're trying to plot some points, right? So Liam's got us f of -4, please.
3 -4.
So if we plug that in, we get an output of 4. That means I have a coordinate point of -4, 4. Fabulous. We have symmetry along the y-axis. So if I have the coordinate point -4, 4, if I flip that over the y-axis, what other coordinate point do I also have? 4, 4. So I also immediately know that f of 4 is equal to 4. So I have another point. I gotta scoot this over. That's right here. Do you see how that's reflected over the y-axis? Knowing that symmetry gets us to take some shortcuts here. Okay, I have information on the left side of this vertical asymptote, on the right side of this one. Do I have enough information in here? Yeah. We need an additional point like in between these two numbers. What's a nice neat number in between -2 and 0 I can use? -1. So let's do f of -1. Same thing, we plug it in. 3 times -1 squared, in parentheses, over -1 squared, in parentheses, minus 4. We should get -1. Yeah. Now, again, if I have this coordinate point, -1, comma, -1, what is the other coordinate point I have by symmetry? 1, comma, -1. So I have this coordinate point as well. At first, it does not look like that is enough information for us to be able to graph all of this, but I promise you it is. Let's start where the most information is. In my mind, we have the most information right here. If we start to play connect the dots, we have to connect like this, and then we cannot cross that vertical asymptote. We have to connect like this, and then we cannot cross that vertical asymptote. Middle looks pretty good. So on the sides, if I go from that 4, 4 point and I go towards my end behavior, towards that horizontal asymptote, it gives me a clue about the way the graph should look. And same thing on the other side. Start at an additional point, go towards your end behavior, and then follow the opposite direction. Voila! That's our fully graphed rational function.
So if you put that in the calculator, that's what it would look like?
Yes, it would not have, in the calculator, it would not have the dashed lines for the horizontal asymptote and the vertical asymptotes. That's why it's helpful that we're graphing it. Otherwise, it just looks like 3 different bowls along the graph. I don't know what to call those. I call them bowls. Okay, we've seen 2. What are our questions? Like I said at the beginning of class, it's not that it's hard, it's that there's lots of small details. Probably the hardest part is playing the connect the dots at the end. But can we individually do all of those rainbow pieces right there?
Yes.
Yes. Do you want to do one more together, or do you want to try one on your own?
Let's do one more together.
Sure, sounds great. Here we go. We have this rational function, f of x equal to x to the 4th power over x squared plus 1. In my 6 steps, what do I start with? Symmetry. So I'm looking for whether it's symmetrical about the y-axis or the origin by plugging in -x. This is -x to the 4th power times -x squared plus 1. But a negative times a negative times a negative times a negative is a positive. And then I have this. So what kind of symmetry do I have? It's an even function, which again means I'm going to be able to balance points along my y-axis because it has y-axis symmetry. Okay, step 2 is to do what? By doing what? Fabulous. We're going to plug in 0. This is 0 to the 4th power over 0 squared plus 1, which is 0 over 1, which is 0. Okay, great. What's the next step? X-intercept. Now remember, x-intercepts are setting the numerator equal to 0. Don't work too hard on this step for this problem. If you do x to the 4th power equals 0, what is x? 0. The 4th root of 0 is still 0. So we have 0 as my x-intercept. Then we're finding the vertical asymptotes. We find the vertical asymptotes by setting the denominator equal to 0 and solving. Walk me through these steps here. What do I do first?
Plus 1.
Are you sure?
No,
Minus 1, okay.
And square root.
And square root. Uh-oh.
I.
We have plus or minus I. So question, are there vertical asymptotes in this graph?
No.
There are no vertical asymptotes here. Very good. So if we get an imaginary number, when we pause, we make sure we solved it correctly. And we did. And then we're like, just kidding, there's no vertical asymptotes. Next step is to find the horizontal asymptotes. We ask ourselves, Bobo, Botan, or Betsy? Yeah, the degree of the top is 4, the degree of the bottom is 2. So this is a Botan graph. So there are no horizontal asymptotes. Whoa, this is going to be weird. So again, before we start the last one, let's put all the information we have on the graph. We know that we should be able to reflect coordinate points across the y-axis. We know that there is a y-intercept at 0, but there's also an x-intercept at 0. I can't draw any vertical asymptotes, and I can't draw any horizontal asymptotes. So that's all I can put on my graph.
That's it? Yep.
For now. But we need information about the pink points. So let's just pick some nice, neat coordinate points on each side here to see what this graph would look like. What's a coordinate point y'all want to plug in?
4.
Sure, let's plug in 4. If we go to plug in 4, actually, can we pick a smaller number? Because we'd just be doing 4 to the 4th power, and I don't want to divide 64 by numbers. So let's pick a smaller one. How about like 1?
1. Why?
Isn't 1 just a little bit to the other side of that 0?
A 2.
Well, let's just, okay, we can do 2.
Okay.
I'll meet you in the middle. Let's do 2. F of 2 would be equal to 2 to the 4th power over 2 squared plus 1. 2 to the 4th power is 16.
Yeah.
2 squared is 4. 4 plus 1 is 5. So we have 16 over 5, which is approximately what?
3.2.
3.2. So I know that I can plot the coordinate point 2, comma 3.2, and we're just going to do our best.
Okay.
Now again, we get lucky with this problem because there's symmetry. Since I know 2, comma 3.2 is a coordinate point, what's another coordinate point?
Negative 2, comma 3.2.
Negative 2, comma 3.2. So if I plot those, that's like a good amount of information here
Yeah.
to draw our rational function.
So it's quadratic.
It's not a quadratic, it is a rational function that appears quadratic in the graph. And that's because it's a degree 4 divided by a degree 2. What's 4 minus 2? That would be a quadratic if you do 4 minus 2. Because you're actually dividing these things. 4 divided by 2, 4 minus 2 is 2. Don't worry about it. Don't worry about it. Okay. That's what I'm going to be asking for you to do, is to graph these kinds of functions. But finding all of the bits of information is a very helpful way to do this. That's a great question. The last thing we're doing today is talking about a specific type of horizontal asymptote. Actually, that's a big lie. It's not called a horizontal asymptote. It's called a slant asymptote. So a slant asymptote is an option for the green step.
Okay.
When I'm talking about the end behavior, when I'm talking about the horizontal asymptotes, there's particular types of graphs that have what are called slant asymptotes instead of horizontal ones. Specifically, these are going to be graphs that are bigger on top by 1, bottom by 1. They don't have horizontal asymptotes, but they'll have slant asymptotes. To find the equation of a slant asymptote, we have to do division.
Yay.
If you can use synthetic division, use it because it's much faster. You will find the equation of the slant asymptote, which would look something like this. This might be helpful to highlight. See how at the end we're getting close to the slanted line instead of a flat line? That's a slant asymptote, and this is going to occur on bigger on top by 1s. So if you notice it's bottom by 1, you can find the linear equation of the slant asymptote by doing division.
It's only on bottom?
Only on bottom by 1. If it's bottom by 2, there's no slant asymptote. That's why our graph we just did didn't have a slant asymptote, because it was bigger on top by 2.
Okay, so it has to be by 1.
Specifically by 1. The one thing I want to bring to your attention is when you finish this division problem, we always had our remainder, cute, and we had our quotient, amazing.
Wow.
I do not care about the remainder.
Oh.
Your slant asymptote is only the quotient part. Do you see the plus 2 over x minus 1 in this answer? No, we just straight up let it go. We don't care. For slant asymptotes, if it's a division question, I do care. So if I was finding the slant asymptote for this graph, f of x equal to x squared minus 4x minus 5, I notice that it is bigger on top by 1. See how it's degree 2 here?
Yes.
Degree 1 there?
Yes.
I want you to write that down, that it's specifically for botten by 1 is when we can do synthetic or long division to find the slant asymptote. Help me set up this this synthetic division though. This is when I can use synthetic division for, because the quotient is like x minus a number or x plus a number, nothing fancy. What number do I put on the outside for my divisor? 3. What are the numbers for my dividend?
1, negative 4, negative.
Fabulous. The steps were bring down, multiply, add, multiply, add. Why did I put plus?
Isn't it negative?
Yep, thank you so much. That felt weird. Okay. Nice, nice, nice. So again, this answer in a division problem, you would have to include the remainder. But for a slant asymptote, we straight up do not care about that remainder. All we care about is the quotient, so that our slant asymptote equation line would be x, 1x, minus 1. That's the equation of the slant asymptote, SA for slant asymptote. So if your graph happened to have a slant asymptote, instead of just drawing a horizontal line at whatever number, you would draw a linear line that had a slope of 1 and a y-intercept of negative 1. So it gives us, again, an additional piece of information on that green step if your equation happens to be bigger on top by 1. Instead of just straight up saying there's not a horizontal asymptote, you can tell me more information, which is great. But not if it's bigger on top by 2. Like our problem on the other page was bigger on top by 2. We didn't have to do a slant asymptote because those don't have them. Okay. You've just listened to me for a long time. You have the rest of the class period to work on what you need. I recommend working on this homework assignment first. So open up your homework, go to section 3.5, and let's get started. So while we're thinking about this, we can start asking additional questions.